This video brought to you by Caped Darth Vader, who seems to be undamaged, although that face looks kind of damaged. But if you remember what happened to Anakin at the end of that one Star Wars movie, he was pretty damaged. Okay, so we're going to solve trigonometric equations in section 7.5. So let's remind ourselves of a couple things first. And that is, what are the main ways we can solve any type of equation, ignoring that it's trig. So one way is an analytical method. Oops, only one L there. Sometimes we call this algebraic. Boy, that's a hard one to spell for me at the moment. So that's one method. Maybe you're factoring, maybe you're completing the square, you're collecting variables on one side of the equation, using inverse stuff, dividing, multiplying, all that kind of mess. And then the second main method is a graphical approach. And there are two ways we could do the graphical approach. One method is what we call the intersection method, or that's what I've been calling it. So if we have like y1 equals y2, you graph both sides and see where they cross. The other method is the intersect method, meaning you say y1 minus y2 equals 0, and you find the x-intercepts. I tend to prefer this method because it's easy to find things on the x-axis, where in the intersection method, you kind of have to search around on the graph to find where they cross. It's not overly difficult. It's just another method. Okay, so I am going to demonstrate all the analytical methods. And then after that, I'm going to show the graphical method. We'll just graph it in Desmos and find those solutions. Okay, so let's recall, what is a trig equation? Note, this is not a trig equation. This is an identity. Boy, spelling is not my day today. Good thing I'm using an erasable pen. This was Allison Price gave me these pens. They are fantastic. This is an identity because x is really all real numbers. That's our solution there. So what is an equation? Well, this would count as an equation. Sine squared of x equals 1. And the reason this is an equation is because it's not an identity. This is not true for all values of x in the domains of sine or cosine. In this case, in the domain of sine, this is true for a set amount of values. So only true for a specific set of x's. All right, what's the end product? Note, if this is the thing I'm working with, the end product is an angle. Angle that makes the statement true. Okay, so in general, the analytical method is to get one trig function. We want trig equals googly gump, preferably some sort of number, and then we would say, so it would look like trig of some x value equals googly gunk, so then x equals trig inverse of googly gunk, and there's your answer, whatever it may be. If we can use unit circle values, in other words, if these are nice ratios from a unit circle, you would be expected to provide the exact values from the unit circle. If not, we would use our calculator to get the approximate values. So let's check out our first option. Oh, look at this wonderful example. It has a trig function equal to a value. So we've already done pretty much all of the analytical work we need to do. All we have to do is solve it. And all we have to do is take the inverse of both sides. So the inverse function we're going to take is inverse of cosine. So x equals cosine inverse of x. Okay, why did I write x? Good Lord. So that is inverse of root 3 over 2. Okay, I know this is a unit circle value. So let's look at the unit circle, and let's see all of the places where x is a positive square root of 3 over 2. I know there's one right here that corresponds to pi sixths. That's square root of 3 over 2 is the x coordinate. the y value is 1/2. So I know one solution here happens to be exactly pi sixths. I know another place where I see that root 3 over 2 is here in the second quadrant, but there it's a negative root 3 over 2, 1/2. That happens to be 5 pi 6. That's not a solution. I know there's another one here. Here again we get negative root 3 over 2, comma 1/2. This one is 7 pi 6. Is that right? Yeah, this one corresponds to 7 pi 6. That's not a solution. And finally, there's one last option over here. This one is a positive. Oh, by the way, I forgot to make that negative. This is a positive root 3 over 2, and that's a negative 1/2. This one is, oh, it's not 9 pi 6 because that would be 2 pi thirds. It's 10 pi sixths. No, it's 11 pi sixths because we're a sixth away from 12 pi. So the other solution is 11 pi 6. Now there's a problem, right? This thing, we can get infinite amount of angles just by spinning 2 pi around this pi 6. So not only is pi 6 a solution, so is this one that corresponds to 13 pi sixths. And we could keep going more and more and more and get infinite coterminal angles. So the way we would account for this is we'd say pi 6 plus, I think your so I believe your textbook uses a K. So we're going to do 2k pi, where k is an integer. So this is the symbol for integers. It's that little z thing. And then 11 pi 6. So note this expression represents all coterminal angles related to the pi sixths, and this next expression would be all coterminal angles related to the 11 pi 6. And note that these two angles are not coterminal. This angle, if we look at it, has a reference angle of pi sixths, but it's on a completely different rotational deal. So let's look at the graphical solution of this and see why we have these infinite amount of solutions showing up. So here comes Desmos. Oops, I thought Desmos was coming. Here it is. And we're looking at, this time I'm going to do the intersect function. So we're going to say f of x equals cosine x. And then we're going to say g of x equals the constant function square root of 3 divided by 2. And here you can see these coterminal angles showing up. And we could zoom out a little and start to see all of them. So if you look at this pi 6, it has a coterminal angle with with 13 pi 6, which is this one here. And then it also has a coterminal angle in the opposite direction of negative 13 pi 6. Yeah, that's right. And then this 11 pi 6 is coterminal with negative pi 6 and negative 13 pi 6. Okay, I was wrong in that last one. So you can look at the hump. That's a helpful way. So these angles are all coterminal. We could hide those, and then we could show these angles are all coterminal. And then if we zoom out just a little bit, you see that just goes on forever and ever and ever. And that's the idea of a rotational or circular function. Okay, so let me show you how I would expect you to draw this by hand if you were taking this a paper exam for me or working on homework. I would expect to see something of this nature. And your cosine deal, that's a really bad cosine. And then you're this thing, and then I'd want to see that this was pi sixths, and that this was 11 pi sixths, and you could show some of the other ones if you wanted to, but this would be enough for me don't put y there, that's crazy, to show that you had done the intersection method. Okay, let's do one more. So this one, we now have a new thing added to the equation. It says in the interval 0 to 2 pi inclusive of 0. So this now says, let's just look at one period of the graph, because we know without this, every time we solve these equations, you're going to have an infinite set of solutions. So this is helpful. It makes us only look at one little set. Okay, so first thing we have to do is subtract 3 from both sides. So we're going to have sine of some value equals, shamefully, I can't do this in my head, 2.0816. I'm getting negative 0.9184. And then we're going to take sine inverse of that. Now, recall that Desmos in our calculator will give us either radians or degrees. Because this has been asked, because the restricted interval is in radians, we should provide radians for this. So let me switch to Desmos real quick, and let's check out what those solutions are. In other words, because I don't know this one, sine inverse is not a special unit circle value, I have to use Desmos to get this approximate value. This still counts as an analytical method. I'm getting, just to make sure everyone notes that we're in radians, not degrees, it's either 66 point whatever or approximately 1.164, negative 1.164 radians. Now, let's go back and look at what this means. Is that the only solution? So I will draw in the unit circle. Recall that the outputs of sine inverse, the only possible ones are in the first and fourth quadrant. So the measure I've got for this one, remember it was like 66, so if this is 45, this is like 66 degrees kind of idea, negative. This would be the radian measure I've got, negative 1.164. So there's another value that our inverse trig function will not give us because it only gives us outputs between here and here. That was so that we would have a function that was one-to-one when we restricted sine. So the other option is this one right here. The question is, what is that angle measure? Well, I know that from here to here is negative pi. So I have chopped off this much to get this other amount. In other words, this amount, I need to add this value to pi. So the other angle is negative pi plus negative 1.164. Now there's two ways we could write it. This way I'm writing the negative angle from here to here, so that negative radian measure, but we might prefer this radian measure from here to here. Well, I know that the entire thing is 2 pi, so we could finagle our way around and get it, but I think it's okay if we just figure out this one. It just occurs to me that this is not correct. I should really be subtracting that angle. Otherwise, we're going to get an angle larger than pi. So let's get this approximate value. I'm just going to use my calculator here, so it's real quick. I don't have to change my screen. I'm getting a negative 1.976. Okay. Oh, wait a minute. These are supposed to be between 0 and 2 pi. So all of the angle measures I found are completely wrong, right? So let's convert it to be between 0 and 2 pi. So the way we do that, I'm going to redraw this because I just made a wreck of everything, right? Here's that first one, which was measured this way. I want to measure it this way. So this is the negative 1.164. Well, what this angle is if I want to get it in terms of 2 pi, I've got this much as negative. If I subtract that from 2 pi, I will get the value in this direction. So 2 times pi minus 1.164, and I'm going to get that angle measure in radians is 5.119. And then the other one, which is this one, what I found was that this measure here was negative 1.976. So we'll do the same thing. This whole thing is 2 pi. So we'll do 2 pi minus 1.976, and we'll get this angle measure. 2 pi minus 1.976 equals 4.307 radians. Hopefully that makes sense to you, that this angle measure is a smaller measure when we look at the positive direction than this one. Okay, so we have now trapped our values between 0 and 2 pi. By the way, if you want to know what 2 pi is as approximation, that's 6.283. So 4.307 is less than that. 5.119 is also less than that. So the correct answer are these two values. Now, if we had not had this restriction, we actually could have just taken these and added 2k pi to them, and we'd have all possible values. Let's note this in Desmos and ensure that I did this right, because it feels like maybe I did something wrong. So I am going to use let's do the Intercepts method, meaning where does this cross the x-axis? Now look at how lazy I am. I'm typing +3, and then I'm going to subtract 2.0816. I'm not even going to simplify that. And we're just going to call this f of x. And then all we're looking for is where does it cross the x-axis. Now we know that the maximum value we can use is up to 2 pi. So I know from 0 to 2 pi, this is the only interval of solutions I'm interested in. So here's one and there's the other. Oh, beautiful. Those are the exact same values I wrote down. So I'm going to draw my graphical solution to prove to whoever's evaluating your work that you actually graphed this and how you found the solutions. So I'm going to, and this time I'm going to include the y-intercept here of 0.918, and then should I show this maximum? I don't know that I would care to, whatever. It's going to look like, and then I'll put in these two values, 4.307 and 5.119. So interesting that this one is a little bit off, or ours is a little bit off because of rounding, right? So probably the correct answer here is 4.06. I think sometimes if you zoom in, you can get a few more decimal places. Yeah, there you go. So here's 4.306. So when I'm zooming way in, so you're gonna, yeah, it's not giving me any more decimal places. That's a rounding error for us because we wrote down 4.307. Remember, we rounded this to 1.976, which it's actually if we had included more decimals, we would have gotten the same answer here. So maybe I should change this to 4.306. Okay, here's my graphical method and my analytical method.